Hello, AIAA. We are the University of Texas at Austin, and today we are very excited to present to you the Penguin. My name is Catherine. I'm the project manager, and today we have speaking Evan, the chief engineer, Alex, the props engineer, and Anna, our structural engineer.
The Penguin aircraft was a 3D printed aircraft made out of nylon 12 carbon fiber filament. The aircraft was 3D printed this year because of UT's restrictions on undergrad access to the lab, which made the team unable to get into any lab space to work hands-on with the aircraft for the entire fall semester, plus spring semester until late March, early April. You can see here one of our work days of us assembling the aircraft. The aircraft takes roughly 30 hours to print all the pieces. This includes horizontal, vertical stabilizers, the wing, all of fuselage sections, landing gear, and a bunch of other miscellaneous components needed for the internals of the aircraft. It takes roughly 5 to 9 hours of assembly to completely assemble the aircraft and wire it to make it flyable. We have our 3-view comparisons here. Overall, our aircraft from tip to tail is 64 inches with a wingspan of 5 feet. It has an enlarged horizontal and vertical stabilizers. These were enlarged because the sensor deployment mission, having a mass of a significant percentage of the plane's overall weight so far out the back of the plane significantly moves our center of gravity. And so to account for this, we enlarged these two surfaces to counteract the stability concerns that might have. So you can see we have our right side view right here. Our aircraft pretty closely follows our 3 views that we submitted in our design report, following the overall design pretty closely. Obviously, modifications were made when manufacturing, such as the exact location of the landing gear, changing based off of CG measurements and balancing to make sure the aircraft was stable both while flying and on the runway and could take off successfully. The overall control architecture for the plane is very simple. We use a set of a bunch of servos that are all wired into a receiver that can be actuated remotely. And these servos actuate control horns on the different control surfaces, which allow us to control the aircraft's path in flight and its stability characteristics and everything like that.
So the propulsion subteam decided to select a single tractor motor with the 15x10 propeller configuration. The specific motor was selected after conducting analysis using MotoCalc and MATLAB to be able to determine which motor would have the best thrust and minimum current draw. The plane itself was powered by a single 6-cell LiPo battery and an electronic speed controller.
There were 2 major trade studies that affected the overall aircraft design, both of them relating to the Mission 2 and Mission 3 requirements. The first trade study was for the sensor design. We ended up going with a condensed rocket design because it maximized the manufacturability, assembly and integration, and aerodynamic efficiency figures of merit that we were looking for. With this condensed rocket design, the one point of concern that we had was that it only had 1 set of horizontal stabilizers to improve stability while it is deployed, but we ended up going with this because of the other pros that it presented with the manufacturability and its assembly and integration into the deployment mechanism. With the deployment mechanism design, we went through a similar trade study where we looked at the reliability, the assembly and integration into the fuselage, and the drag that would be produced by the sensor being integrated into the deployment mechanism. For this system, we ended up going with the ramp design because of the ease and quickness that the sensor is able to slide off of that ramp. As you can see in the image, there's really not any way that the system could fail, which was desirable for the reliability that it presented. The con of this design was that it is a little bit bulky, but we ended up just kind of having that comply with the overall aircraft design. With that being said, these 2 systems did contribute to the overall aircraft design. The fuselage was designed to have a rear back door that was open and wide enough for the mechanism to fit through it so that it could be easily assembled into the fuselage, and also large enough for the sensor to easily deploy out and be retrieved easily.
The overall mission performance predictions for the Penguin aircraft were calculated based off of information gathered from previous year's competition, taking into consideration the maximum speeds, ground mission times, and other characteristics from past competitions that UT at Austin DBF has participated in, and using those as benchmarks to make rough estimations for the overall expected best aircraft for each mission, and to help normalize our score to give us a reasonable approximation. Overall, missions 1, 2, and 3, the aircraft weighs roughly 8, 18, and 9 pounds respectively. And based off of our propulsion system and battery pack, our aircraft has no problem with in the endurance sections of each of these missions with flight speeds of 105, 95, and 72 miles per hour. Overall, our final score after normalization, we approximate to be 5.7. Thank you.